We step into a crowded room and instantly map the space. We recognize faces, gauge distances, and isolate individual voices effortlessly. But that subjective experience of reality shatters the moment you examine the raw physics of perception. That effortless experience is an illusion. The physical hardware of the human eye and ear do not see chairs or hear voices. Your sensory organs are biological transducers. Their only function is to measure raw physical energy from the environment and convert it into numerical data. This matrix represents the actual data output of visual perception. When photons hit the photoreceptors at the back of the eye, they are converted into a spatial array of electrical voltages. What travels down your optic nerve looks exactly like a digital camera sensor, an updating grid of numerical values. Simultaneously, the auditory nerve transmits its own data stream, compressing acoustic energy into a one-dimensional time series of numbers. A numerical grid and a 1D timeline of pressure waves do not contain sufficient mathematical information to describe the physical world. To extract a three-dimensional reality from this data, human perception operates as a massive computational engine, calculating what caused the input rather than acting as a passive recording device. Before those biological transducers can extract any data, they are strictly bound by the physical constraints of how energy travels. Raw energy requires a physical medium to move from a source to a sensor. Transmission fails without a medium. In the total vacuum of space surrounding this satellite, the lack of air molecules makes acoustic propagation impossible. Inside a dense medium like the Earth's atmosphere, vibrating objects push against surrounding air molecules. This creates longitudinal waves of alternating compression and rarefaction that project outward. The speed of this wave is governed entirely by the medium's density, not the intensity of the source. Sound waves push through room temperature air at exactly 343 meters per second, regardless of whether the source is a whisper or a loud shout. By the time this mechanical wave strikes the eardrum, it is merely a delayed, fluctuating pressure state. The data arriving at the brain is entirely devoid of inherent object identity or meaning. Processing this raw sensory input immediately traps the brain in an algorithmic bottleneck known as an ill-posed problem. An ill-posed equation lacks information for a single correct answer. Given x plus y equals 10, valid solutions are infinite. Visual data suffers identical ambiguity. A 2D retinal footprint lacks a z-axis, meaning infinite 3D geometries project the exact same flat image. Auditory perception faces a similar data collapse, most clearly demonstrated by the dense acoustic environment of a cocktail party. A room full of clinking glasses, background music, and overlapping conversations generates dozens of distinct acoustic events, but all those independent waves are forced to mathematically sum together at the eardrum, collapsing into a single, highly complex pressure variation. Because physical reality undergoes massive data loss before it ever hits the nervous system, there are infinite possible physical realities that perfectly match any single moment of sensory input. Identifying objects from incomplete data is difficult, but the biological network must also overcome a secondary computational hurdle, known as invariance. Invariance is the required ability of a system to extract a constant, stable identity from input data that is constantly undergoing massive physical distortions. This rotating wireframe shows how physical movement scrambles visual data. As a vehicle moves, the matrix of pixel values hitting your retina changes completely. An object viewed closely in direct sunlight produces a numerical footprint totally distinct from the same object viewed at a distance in the evening. The acoustic equivalent of this distortion happens every time a speaker moves from a dry acoustic environment into a highly reverberant one. These comparative spectrograms show how environmental reverberation physically smears an acoustic structure over time. The geometric pattern of the data is severely distorted, yet a human listener easily recognizes the same words. Biological networks must possess specific algorithms capable of ignoring these massive physical distortions, discarding the noise to extract an invariant interpretation of reality. The theoretical solution to how the brain clears these computational bottlenecks was established by 19th century scientist Hermann von Helmholtz. He defined the brain's algorithmic solution as unconscious inference. Helmholtz deduced that to solve mathematically unsolvable sensory equations, the brain applies strict statistical priors. It relies on assumptions forged by biological evolution and the learned physics of the real world. This inverted point light walker fails to trigger probabilistic assumptions, appearing as random noise. Rotated to match gravity's baseline expectations, a clear human identity instantly focuses. You do not passively observe the walker. Your brain mathematically calculates their presence by applying a rigid, pre-programmed physical model to a sequence of ambiguous white dots. Researchers use optical and auditory illusions as diagnostic edge cases to study perception. Illusions occur when an artificial stimulus is designed to perfectly misalign with the brain's highly optimized probabilistic assumptions. This diagram isolates a 2D geometric path to reveal how the brain computes depth. If we trace the physical trajectory of the ball, it moves in a strict, flat horizontal line across the screen. The only changing variable is the path of the dark spot beneath it. Because physical objects cast shadows relative to their elevation, the brain automatically calculates the missing z-axis by tracking the geometric proximity of the shadow, forcing you to perceive a 3D arc through the air. This computation extends to material properties. In the Adelson checkerboard, if we mask out the surrounding context, we prove that a square in the apparent light and a square in the shadow share the exact same numeric grayscale value. But when the full image is visible, the brain detects the shadow, infers a lower ambient illumination level, and algorithmically adds a lighter pigment value to the object to calculate its true physical color. The same rules apply to auditory processing. If an intense burst of noise interrupts a continuous texture like applause, the brain calculates that the original acoustic data is simply being masked and algorithmically fills in the gap. These edge cases reveal perception as a series of hard-coded algorithmic deductions rather than a transparent window into objective reality. To understand the precision of these deductions, we must look at how humans mathematically measure the intensity of the physical energy our sensors collect. In acoustics, sound power and pressure levels are measured using the decibel scale. This graph charts the decibel scale. It is not a linear measurement, but a strict logarithmic ratio. It compares the intensity of a sound against a biological baseline, the absolute quietest pressure variation a human ear can detect. Every 10 decibel increment represents an exponential 10-fold increase in actual physical power, scaling rapidly from the rustling of leaves up to the 140 decibel blast of a military jet taking off, the threshold where acoustic energy translates into physical pain. This overlaid data shows why scientists use a logarithmic scale. It directly mirrors human biological discrimination thresholds. The minimum change in intensity the auditory system can detect is 1 decibel. That biological resolution tracks perfectly with the mathematical log scale across all volume intensities. Human biology operates as a logarithmic processor. It compresses extreme variations in physical energy into manageable, calculable intervals. The math confirms human beings do not directly experience the raw physical data of the universe. Conscious reality is a highly processed, probabilistically inferred simulation built by unconscious inference. For decades, computer scientists attempting to program machines to parse this sensory data considered the ill-posed problem to be computationally insurmountable. That barrier was broken by the development of artificial neural networks. By reverse engineering human biological perception, engineers structured AI systems with similar mechanisms, filtering, pooling, and normalization, to finally achieve invariant recognition. Deciphering the mathematical algorithms of our sensory hardware provided the blueprint for machines to finally perceive the world.